Good evening, friends. So today's webinar is about uh, adaptive boosting. I believe there shouldn't be an echo right now. So today's webinar is all about your one of the boosting techniques, which is called as your adaptive boosting. Now, before we discuss about adaptive boosting, we have something called as boosting. So what exactly does boosting means? So in order to understand boosting, there's a saying over here which says mistakes are meant for learning and not for repeating, right? So you can say in a way that boosting follows this particular saying. So how is it learning from the mistakes and not repeating from the mistakes? So this is the easiest way to remember the boosting technique. Now this is one of the ensemble techniques, right? So what are ensemble techniques? Ensemble techniques are nothing but they are nothing but a combination of multiple classifiers that you have. So the term boosting, it says that the term boosting refers to a family of algorithms which converts the weak learners to strong learners. What do you mean by weak learners and what do you mean by the strong learners? So yeah, so the term boosting refers to a family of algorithms which converts the weak learners to strong learners. So what do you mean by weak learners? Weak learners is nothing but your weak classifiers, right? So you have the classification techniques. You have got multiple classification techniques, right? Supervised learning techniques. So this is one of those machine algorithms. So whenever you build any algorithm, you may expect a higher accuracy or a lower accuracy. So the weak learners are nothing but the models which are giving you lower accuracy, right? So it converts these models into the strong models. How is it doing? So boosting is an ensemble method for improving the model predictions of any given learning algorithm. Now, the idea of boosting is to train weak learners sequentially, each trying to correct its predecessor. So how does it does? So you can see over here, there's an image over here which says that there's one learner and something written as single over here. So this is nothing but you can just relate it as a decision tree supervised machine learning algorithm was built. Only one classification model M1 has been built over here. Now you have got an ensemble technique called as in bagging, right? So bagging is another ensemble technique that was being implemented on the same data set, and now you have built 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So 11 particular models were built using bagging technique, and you are coming up with some classification by taking an average or the mode of that classification technique. This is bagging. But what happens in boosting? So boosting is nothing but it is again made up of these 11 models, be it 11 or more or less. So you have got again few models, decision trees being built over here, but then it is not going to compute the average, right? It is not going to compute the average of all the models, or it's not going to take any mode of all the classifications, right? So that is not the way how boosting works. So sequentially, it says that the idea of boosting is to train the weak learners. So for example, out of these 11 models that you have, there could be some models that could be weak, there could be some models which are strong. So what do you mean by weak and what do you mean by strong? Weak are nothing but the models which are having lesser accuracy. Lesser accuracy is equals to higher misclassification, right? So you have classifications, you have got the labels in your output variable. So these weak learners will have got higher misclassifications. They are, for that reason they are called as your weak learners or weak classifiers. Now let us come to your adaptive boosting. Your boosting is a family of ensemble algorithms that builds a strong classifier out of a number of weak classifiers. This we already have discussed. Now these are the major boosting techniques that we have in the family of boosting algorithms, which is AdaBoost, called as adaptive boosting, gradient descent, and XGBoost. Major ones. There could be other boosting techniques available, but these are the major ones which are predominantly used. If unmuted. Fine. Now, how do these bagging and boosting get the learners? What do you mean by n over here? N is nothing but what is n? N over here is representing the sample size, right? So you have a population data. From this population data, what are you going to do? You're drawing random samples, SRS. Write it over here. SRS using simple random sampling. What are you doing? You're drawing multiple samples over here in this way, right? So on those samples, you're employing decision tree. For example, if you're employing decision tree, you'll be getting different classifications and different equations on these samples. So what does this algorithm does is, new training datasets are produced by random sampling with replacement from the original dataset. So what do you mean by with replacement? For example, if you're drawing this is your population data, and it has got a lot of data points over here. Say it has got 1,000 data points. Now out of these 1,000 data points, you're supposed to collect a sample of say 200, right? So in that way, you'll have to come up with say 11 samples. So sample 1, sample 2, sample 3, and so on will be collected. So once this sample 1 is collected with 200 data points, these 200 data points will be put back in the population data, and again when the sample 2 is been picked, these 200 data points have an equal opportunity to be picked once again. So again, when the SRS happens, maybe in the rarest of the rare scenario, you will be getting the same data points, or else some other data points, or else a mixture of these data points with some other data points, right? So that is called as your with replacement technique. So you have got with replacement, and you also have got without replacement. So it depends upon you how you employ the with and without replacement. It again depends upon the size of the population data and your size of the sample size that you are drawing. So in the case of bagging, any element has the same probability to appear in a new dataset. For boosting, the observations are weighted. So you can see over here, this is your single classifier, right? So this is your training dataset, and here you have got the boosting, the bagging, and bagging over here, all the data points, the size of all the data points, all the observations are more or less are almost the same, right? Now for in boosting, the observations are weighted, and therefore some of them will be part in the new sets more often. So there's something called as weights will be assigned to the observations. Weights will be assigned to observations in order to pick. So you can see that some of these observations are, the size is bigger and some of them is smaller. So how does the weights get, allocated to these observations? That we'll discuss in a while. So we know that it employs simple random sampling, and using the simple random sampling technique, it picks up the observations. Now, how are these observations or the data points weighted? Now over here in your bagging model, wherein you perform in a parallel way, what happens is you, from this population data, you draw a sample over here S1, and then over here S2, you S3. In that way you come up with n samples, right? Sn. Now you build a classifier on this M1, you come up with M2 here, you come up with M3 and Mn. Now M1, M2, M3, Mn, all of them are independent of each other in your bagging technique. They're not related. Even though you can have observations which may be similar in those samples, but again the classifiers are very much different. So all of these classifiers are different, and finally what you do is you take an average or you take a mode over there. But in boosting algorithms, each classifier is trained on data taken into account of the previous classifier success. Now what does this mean? It means that, let me just erase and draw it once again. Say out of this population data, you are building a sample, right? Now this sample, will it give you 100% accuracy? No, right? So you cannot expect 100% accuracy from this sample. A model is built. Now this model cannot give you 100% accuracy. So what you do is, there will be some misclassification. Say you have got out of 100 observations, there were 100 observations. Out of 100, your 80 observations were true. I mean, the correct classification happened, and then you have got 20 observations which were misclassified. Now, you know that 80 of them have been properly classified. In the second sample, what happens is, these 20 observations which were misclassified will have a more advantage or even more weightage. Initially, in the first sample, equal weightage will be given for all these observations. Say you're drawing an observation of this, from this 1000, you're drawing an observation of 100. Now these 100 will have equal weightage earlier in the first sample, but what happens in the second sample is, these 20 misclassifications have happened over here. So these will have more weight. When they have more weight, they will have more chance in getting selected. So obviously here these 20 will be selected, and the remaining 80 may be selected from here, or they can be selected from others. So you'll be getting 80. Now a model will be built, M2, and say over here you have got 85 observations which were properly classified, and there were 15 observations which were incorrectly classified. Now what happens is, these 15 observations, whichever they are, will have more weightage to be picked up in the next classifier. So I'm drawing another sample. Now in this sample, these observations will be definitely picked because they have got more weightage associated with them. So these 15 plus 85 that is getting picked from here, together you will have 100 samples. Again a classifier will be built, M3. Now this M3 will be giving some accuracy, maybe more or maybe less. So at times you will also get accuracy of say 70% is what you have got, right? So 70 correct classifications and 30 incorrect classifications. Now these 30 will have got more weightage to get selected in the next sample. So it will be 30 plus 70, and over here just imagine that S4, the model 4, is giving you an accuracy of 95%, right? So this M4 is giving you 95% of accuracy, meaning out of 100 observations, 95 observations were correctly classified and 5% of the observations were incorrectly classified. In this way, the process goes on for all the number of samples that you are drawing and the models that you are building, right? So after each training step, the weights are redistributed. That is what is happening over here. After your each training step, after you get the accuracy, what happens is, the weights will be readjusted. These misclassifications observations will be having more weightage than the correct classifications. In that way, what it tries to do is, this is your weak classifier, right? The M1 that you have built over here. First one is a weak classifier. So since you are providing more weightage to these 20 observations, what happens is, in the next iteration you are getting model M2, which is giving you 85% of accuracy. So are you not building a strong classifier from a weak classifier. Then from this 85 percentage of accuracy model, you're giving more weightage to these 15 observations, and then you are getting another model of you're building a model M3 85 15. Then you build these 15 observations have got more weightage, and so you're building another model. So this time from this weak classifier, you again got a weak classifier. This also can happen. But normally what happens is you will be getting in this way, the first in model M1 will be the weakest, then followed by M2, followed by M3, and maybe M4 can be the most weakest, you know, model. Again it improvises. In this way what happens is it makes use of these weights and assigns them so intelligently that the models will be built in such a way that, I mean, they will be just improvising from here. This is, weak classifier. From this weak classifier, you're being, building a strong classifier, and you just proceed further until all the samples. Now, misclassified data increases its weights to emphasize the more difficult cases. Yes, that is what it is doing, and in this way, subsequent learners will focus on them during the training. So that is what is happening over here. That is called as the intelligent way of assigning weights to the observations and selecting the observations intelligently. So it does not do just the average like bagging does, right? So you can see over here, this particular diagram may make you understand even more in a better way. So you have got first single model which is built over here, the decision tree, and one model is being built. Here multiple models 1, 2, 3 are built, and you're getting output from 3 different classifiers. Now over here the first model is built, right? So from the first model you're getting a model M1. This is your sample one. So from this model, based on this model one's output, you will be assigned weight. I mean, the algorithm will be assigning the weights to those observations which were incorrectly classified. More weights will be assigned. Next, again M2 will be built. Now based on the output of M2, the observations which have got which were incorrectly classified will be assigned more weights. So the bigger ones that you see over here are nothing but the ones which were misclassified in the previous model. In this way, this process goes on. This is called as your intelligent way of selecting the observations. Yeah, we'll be coming back to the Q&A session towards the end. Now, how are classifications performed? We know that it is selecting the observations intelligently. So what it does is, this algorithm, robust, it assigns a second set of weights, this times for the n classifiers over here. So it computes the weighted average. You have this E1 classifier, you have got this E2 classifier, you have got this EN classifier. These three classifiers are there. So instead of here, you can see that bagging is taking a simple average of all these classifiers, but your boosting algorithm, your other boost algorithm, it is not going to take the simple average. It is going to take some weighted average. Now that weighted, we know that weights are assigned to observations. Earlier, weights were assigned to observations, but alongside assigning the weights to observations, this algorithm also assigns weights to the models. So some weight will be assigned over here, some weight will be assigned over here. In this way, weights will also be assigned to all these outputs. Then it is going to take the weighted average for all the estimates, right? So it is not that only the observations are getting weights, your model output will also be getting the weights. Finally, it's going to take the weighted average. Now in the boosting training stage, the algorithm allocates weights to each resulting model, and a learner with a good classification result on the training data will be assigned a higher weight than the poorer one, right? So similar to your observations which were incorrectly classified were getting incorrectly classified observations will get higher weights, right? Similarly, better models will get higher weights here. A learner with good a classification result on the training data will be assigned a higher weight than a poor one. So when evaluating a new learner, boosting needs to keep track of learners' errors too. So that is going to be taken care internally. Now, what happens is some of the boosting techniques also include an extra condition to keep or discard a single learner. Single learner is nothing but a model. So out of those 500 models that you build, for example, if 500 decision trees is what you're building, from that it can also discard few of those. Maybe 100 decision trees it can discard. Meaning, if at all, if you're getting an error less than 50 percentage is required to maintain the model. So if you're getting an accuracy which is less than 50 percentage, are you going to keep that model? No, you're not going to keep that model. So you can just remove it from the computation. So those kind of parameters and arguments can also be passed to remove the models which has got a lesser accuracy while computing the final output. So you can see over here, this is the first model that you're building. These are the observations. So these are all the observations. Observation 1, 2, 3, 4, and 5. So they have got equal weights over here. And the first model M1 and the first model M1 has given 69 percentage of accuracy. Right. Now after getting 69 percentage of accuracy, few of these observations were incorrectly classified. So just imagine that the first observation was incorrectly classified over here. For that reason, it has got more weight. More weight meaning it will be definitely selected. And it will be selected maybe more than once in order to train the model in a better way. And these weights which were correctly classified, these observations which were correctly classified has got the similar or the lesser number of weights. And again a new model has been built, and now you have got an accuracy of 97 percentage here. Now what happens is in the next iteration, this observation was incorrectly classified, and this observation were also incorrectly classified, and these were correctly classified. Now in this way, this will have got more weight, and the first and the last ones will have got more weights, and a classifier will be built. Now you're getting 90 percentage, right? So in this way, this process goes on, and the output will be computed based on these models. Now weights are assigned here, and weights are also assigned here. Weights are also assigned to the models. Models weighted average will be computed in order to compute the accuracy and the classifications rather. So weighted average will be performed over here. So how does it start? Each sample have the same starting weight, that is 1 by n. What is n over here? N is nothing but the sample size, right? So if I'm drawing a sample of size 100, so they will be assigned a weight 1 by 100. First, initially all of them will be getting 0.01 is what they're going to get, the weight. And the classifier, the first classifier will be built. Now, after that, based on the output, a weak classifier using the weighted, fit a weak classifier using the weighted samples and compute the case model's misclassification error. Meaning, what it does is, it computes something called as Kate stage. So it gets this error right over here. You get an error, and in order to understand that, let me just take you all over here. Yeah. So here something called as misclassification rate will be computed, which is given by correct minus n. Correct are the number of training instances predicted correctly by the model, and n is the total number of training instances. So out of the, say, 100 observations per day, out of 100 observations, 80 were correctly classified, So you will be getting error as 80 minus 100 over 100. So you are getting an error as minus 20 divided by 100, right? So here we are getting minus zero point 0.2. So the above formula is modified to use the weighted average of the training instance in this way. This formula is being employed over here. This weight this weight will be assigned and the error will be replaced over here. And if I take you back to the previous slide, yeah. So update the sample weights, giving more weight to the incorrectly predicted samples and less weights to the correctly predicted samples. So that is what it is doing. Assign more weights to the wrongly classified observations and more weights to the correctly less weights to the correctly classified observations. So finally, what happens is you will be getting in this way, which is the weighted sum of the misclassification rate, where W is the weight of for the training instance I, and P error is a prediction error. So you will be getting some error for each and every model, right? So it is nothing but you are building multiple models, and for each and every model you have this weight and this weight and the error rate. So weight of that model and the error of that model, right? So in this way, finally the error will be computed, and over here one is considered to be misclassified and 0 if correctly classified. For example, if we had, yeah, we'll come to that. For example, if we had 3 training instances with the weights 0.01, zero 0.5 zero 0.5 and zero 0.2, and the predicted values were -1, -1 and -1, and the actual output in the instances were -1, 1 and -1. This is your actual value, and this happens to be your predicted value, right? So where is the match? So this is a match, right? And here you have a match, and here you do not have a match, right? So how is it getting multiplied? Your weight 0.01 is getting multiplied by 0 because there is a match over here, and -1, this one 0.5 is the weight for that, and it is being multiplied by 1 plus 0.2 getting multiplied by 0. Since these are the correct classification, this is the incorrect classification. Divided by some of the weights, you got an error value as 0.704. Now what is it going to do with this error value? Let us see. Now using this error value, it is going to compute something called as stage value. Now stage value is calculated for the trained model, which provides a weighting for any predictions that model makes. So that is going to be using this expression, natural logarithm of 1 minus error divided by error, right? So after you get the stage value, what you do is you employ the stage over here. I mean, you just have to replace over here, and it says that the effect of the stage weight is that more accurate models have more weights, and this particular expression will be replaced. The stage will be replaced here, and the weight will be readjusted once again, and the weights will be given back to your observations and models. Now what happens is, let us practically implement the same thing in your RStudio. Let me show you all that in RStudio. I mean, we'll try to employ that in RStudio. Just a moment. So what I'm doing over here is, so we all know the iris dataset, right? So based on that iris dataset, we are going to employ boosting or the boost algorithm. And if I just do data of iris, this is your iris dataset, and if I just do view of your iris, it is going to give you the dataset. So this is the dataset. You have got sepal length, petal width, and species. So it has got three classifications here, and Setosa, Versicolor, and Virginica. So you can see that table of iris dollar species is going to give you the proportion. So there are 150 observations, out of which 50 observations are Setosa, 50 are Versicolor, and 50 are Virginica. Now I'm creating randomly sampling the dataset and using the create dataset partition function, which is there in your caret package. So I'll have to invoke this package, or else I can just execute over here library of caret. Fine. So I'm considering 85% of the observations in the training dataset. Right. Now from this iris dataset, I'm considering those 85% of the observations in my training dataset. So this is like an object which was created as to fetch the 85% of the rows, and from here I'm considering those rows in my training dataset. So you can see the view of, just employ view of training. Yeah, training one. So in training one we have the training data. So these are the 129 observations, your trained dataset, and then you have got the remaining observations which are present in the test dataset. Right. So this is your 21 observations from your test dataset. Now I'm building a model C 5.0 on the output variable of interest species using all the input variables, and the data happens to be training data, leaving out the fifth observation, the fifth column. Leaving out the fifth column, I'm considering all the variables from your training dataset. And trials equal to 15 is going to define the AdaBoost algorithm over here. If you do not employ trials, it's not going to employ the AdaBoost algorithm. And there are different functions and packages which are available, which will employ your boosting techniques. So using your C 5.0, you can employ boosting by incorporating this trials argument. Now I said that there are 15 trials that have to be done. So let me execute it. Okay, I'll have to invoke that package as well. Let me execute it once again. Now I have this model. Now using this model, I'm predicting on the your test dataset, which is nothing but the 21 observations, right? So if I just run this, you will be getting the observations in this way, and I'm computing the, you know, comparing the actual values and the predicted values over here, and now you get the confusion matrix in this way. So out of those 21 observations, these are the correct classifications. The diagonals from are the ones which are the correct classifications. 5 plus 6 plus 6 divided by, you have 21 observations. So there were two observations, two from Setosa over here. These are misclassified. These are also misclassified. So you have got 6 plus 6, 12, 12 plus 5 is 17, and there are 17 correct classifications out of 21. So these ones are the rounded ones are the misclassifications. right? So let me just run it. So this is what is going to be the accuracy, and 17 by 21 is 80% of accuracy is what you're getting. So you are running it individually. Now if I show you this fit tree, you can see that number of sample size is 129, number of boosting iterations performed is 15. So what I'm doing over here is I'm repeating this for 101 times, right? 101 boosting trees is what I'm going to perform. So I'm saving it in the object. The accuracy is getting saved in an object, in a list. So first I'll define this list as null, and then I'll just repeat this process 101 times. Right, so this process gets repeated 101 times, and what happens, since this is a very small data set of 150 observations, it got completed very soon. But in real time you will have thousands of observations, and there what happens is it will take long time. So based on that you'll have to take the sample size. Now if you look at the mean accuracy, you will be getting the mean accuracy as 94%. So earlier when you have bit one tree, it's a tree, you have got an accuracy of 80. What was that? 80 percentage of accuracy is what we have got, approximately 81 percentage, right? Trials is nothing but, you're just implementing boosting over here. You can just go to the documentation. I'll just show you in the documentation of the C5.0. If you're not implementing, if you're not using these trials, then it is not going to employ the boosting technique. An integer specifying the number of boosting iterations to be performed, right? A value of 1 indicates that a single model is being used over here. So you're performing the boosting iterations using trial equal to 15. So this is getting repeated 101 times. So out of those 101 results, you got a mean accuracy of 94 percentage. So internally all weights are adjusted, all the uh, weights are readjusted, and the weights to the models are also given. So finally you got an accuracy of 94 percentage. So it has improved from 80.9 percentage to 94 percentage. So the problem over here with, one drawback with boosting technique is it may overfit slightly. It may overfit the model, but it improves the accuracy a lot by intelligently assigning the weights to the observations and also to the models. Right. So let me look at if we have any questions to be taken. Here we are building multiple models in series. Among these models, which one will be the final model? If the nth model is weaker than n minus 1th model, so what happens is it takes Anup, it assigns the weights. It assigns the weights to the to the observations and also to the models. It assigns weights to both observations and the models. Observations are nothing but the ones which are misclassified. More weights will be assigned to them, and more weights will be assigned to the models which have got the higher accuracy. Yeah, errors will be in the input to the next model. Errors in the sense, errors are nothing but the misclassification observations that you have coming in from the previous model. So based on the previous model, the selection of the new observations will happen. Yes. So what what is the difference between bagging and boosting is your bagging algorithm It also does, yes, here 15 times the boosting is done on 101 models. So bagging is being performed individually on different samples, and boosting, these models are not interrelated over here. Once you pick up the sample, the model is built and it just forgets these observations and the model. Again, these observations may be put back, and with replacement, then you'll get a different sample S2 altogether. You build a model. So this model 1 is not dependent or related to model M2, and this sample may or may not be related because you may be getting the similar observations. So you get M3 for S3, and you get S4 over here, and you have M4. Now you just do just an average, or you compute a mode to get the output, right? So equal importance is given each of those models, but that is not the case with boosting. Boosting, what it does, it first looks at the output of model 1, M1. Initially it assigns same weights to each and every observations, then M1 is built, and after that it looks at which of those observations are which are getting misclassified. So those observations will be given more weightage, and less observations, and the observations which are correctly classified will be given less weightage. Then you will be getting M2. Now based on this accuracy, the other model will be built. So this process goes on for all the iterations, and finally again on M1 weightages will be given, and based on those weightages, weighted average of accuracies will be computed. In this way you will be getting final accuracy, which happens to be 94% for us. So is that clear? Yeah, I mean, it is just not, it is just Anup, it is just not that it is applicable only for binary outputs. We have employed it for your uh, more than binary one, more than two categories, right? So here iris dataset has got three categories. Yeah, again you're computing a weighted average. It is not that only the one model which is giving you the highest accuracy, that is not going to be the considered only model which is going to be considered. They just, that will be given more preference, but then what all models you have, you will be, it will be computing the weighted average for all those models. If you are just considering only one model, then it will be, I mean, you're not building any ensemble technique over here. It is like you're just building only one decision tree, right? Yeah, any other questions? With higher accuracy, is there any chance of yes, so absolutely. So what happens is there is slight overfitting can happen over here with boosting, but that is not the case with bagging. Since bagging is, it is giving you equal importance to each of these models. So overfitting is not the case with bagging. That can be, if you have any overfitting problem coming in from any model, be it decision tree or neural networks or SVM, and if you are employing bagging alongside applying, the individual techniques, then bagging will reduce the overfitting problem. But you can see slight overfitting, which is going on in your boosting algorithm. Again, you can just play around with the parameters that you have, and based on that, you can take a call. When there are, like, here there are 180 models. Right? Suppose you want to build different classification models. So you mean to say that you want to build different models, right? You want decision tree as a single model, and you want support vector machine another model, and you want KNN another model, right? In that way, you want multiple models to be employed on different samples. So that technique is called as stacking. You combine the outputs from different algorithms You take the output from the different algorithms, you combine them, and you will be given. That is a different technique. Here only decision tree is being employed. So these are all the enhancements of your decision tree. Bagging, boosting, other boost, your gradient descent. No, bagging is something else. We had a webinar on bagging as well, right? That is not bagging, that is your stacking technique. In your bagging and boosting, you're building decision trees. You're not building support vector machines, or you're not building neural networks. Stacking, it is called a stacking. Is that clear? Any more questions? I mean, we have to write down our own code, Tejaswini. There is no predefined loop that has to be done. We have to write down our own coding in order to combine the output from different models. Individual models have to be combined together using the code that we'll have to write. We have to write down a for loop, and then we'll have to combine the results over there coming in from different models. Finally, you will be giving the output. You can also find out if there are any predefined functions that can employ these things. But as far as I remember, when we do not have any predefined functions, we just have to write down our own function. Okay. Salman says, so boosting or bagging, what it does is, see, your decision tree is going to build a single model, right? One model is what it is going to build. So what bagging does, bagging builds multiple models, right? So here only one model is being, here you have multiple models. But how are these models built? You have your data set, right? From this data set, it's going to draw samples. Sample 1, it has drawn sample 1 of whichever size. Say out of these 1000 observations, 100 observations were built. So model M1 was built, and then model M2 was built using 100 observations. Then again using 100 observations, model M3 was built. Say 10 models were built, M10, right? So it is going to take average of M1, M2 plus so on till M10 divided by 10. You will be getting the average of all those accuracies, right? So you get one accuracy. But what boosting does is, while selecting the observations over here, you have got observations, right? You have to pick sample size of 100. So initially some random sampling will be done, and you will be getting 100 observations. Now these 100 observations will give some accuracy, misclassification, and classification. Say 80 observations were correctly classified and 20 observations were incorrectly classified. So these 20 observations will have more weight. Initially, it will assign the same weight for all the observations while collecting 100 observations. But in boosting, that in the next model that it is going to build, it looks at the output of the previous model. It sees that these 20 observations have got less weight, so they will be assigned more weight, and they will be chosen over here multiple times, and the remaining observations will be also chosen. Now you will have these 20 observations, again you will be getting some accuracy. So you have got say 90% of accuracy. Is it not improving the accuracy by stressing on these 20 observations that were incorrectly classified? So in that way it is going to improve the accuracy. Finally what happens is, you will be getting multiple models, right? You will have multiple models, M1, M2, M3, and so on. Now even these models will be assigned some weights W1, W2, W3 and so on till Wn, similar to your samples. Now weighted average of these estimates will be computed and finally you'll be getting a result in this way. Weighted average of those outputs. So all it does internally, all these things will be done internally using the function. Here simple average is done. Now sample S1 model M1 is not dependent on M2, neither M3 is dependent on M2. But here every model is dependent on the previous model. In this way it classifies and computes the accuracy. Yeah. So put this, but the next sample may not contain the same observations, right? I did not exactly get you, Poonam. Yeah, what happens is, at least you will be, yeah, every sample has different observations, but the ones which were misclassified earlier will be given more importance in getting selected. So they will be certainly selected based on the weights. Based on the weight, selection is happening, so they will be certainly selected. Yeah. So how can we overfit this problem? One thing is, what we can do is, there was a condition over there to trim the models or remove the models which has less accuracy, right? So whichever model has got a lesser accuracy, those models can be dropped. Now if you are dropping the models which has got lesser accuracy, and finally if you're computing the weighted average, obviously you will be getting a higher accuracy model, right? If you're dropping the lower accuracy model, say you have got some model which was less than 50 percentage, right? This was less than 50 percentage accuracy, and you're getting an accurate, if you are not including this, then it means that you're including only the models which has got higher accuracies, right? Now what happens, this is the way how overfitting happens. If you are also including this model over here, then the accuracy of the model is slightly reduced and the misclassification rate will be higher, but then it will be slightly a generalized model, right? So it will be reliable model, but over here you can find overfitting. So do not drop the models which have got lesser accuracy. Try to include those models in computation and see what is the amount of accuracy that you're getting. So in this way you can handle to some extent you can handle the overfitting problem. No, you should not perform individually. You'll be getting the results individually. When you look at the results, you'll be getting the individually. How is it to ensure that misclassified observations are included in that will be taken care automatically by the model. You don't have to declare the observations anew. Misclassified observations will be automatically included by the algorithm itself. We are not going to ask the algorithm to please use these observations as they are misclassified. No, that is not going to happen. That is going to be automatically done by the algorithm. Yeah, because this is just manual code that we have written. So if you go by the functions of the packages which are available, then you will be getting the results individually. So what you can do over here is you can just type in, instead of this, here you just have to put fit dollar of I. In this way, if you just mention predictor of I, then you will be getting the results for 101. So you'll have to employ that. Like what we have employed in your bagging, see over here, we have employed in this way, right? You built a model over here. You have built a model. You're computing different models, and you're building fit.tree on the training data set. By using those models, you're predicting over here. So here for all those number of iterations. So this is the way how you'll have to write down the code manually, or else you can just make use of those functions which are available. You have these functions which are available in carrot function or carrot package as well to implement boosting and bagging techniques. There you will be able to see the results individually. I mean, you don't even have to look at those 100 or 500 models and choose those models which are giving you the least results. You just have to, maybe there will be a parameter for the error or accuracy that will have to define the parameter there, less than 50% please profit in that way. Any more questions? That's what I was said, Kishan, right, just now. You can include the weak classifiers in the computation to handle the accuracy, to handle the overfitting problem. Here is the testing data taken as a sample. Did we not perform simple random sampling over here? Are we not performing a simple random sampling on this iris set to get training and test data? Yes, we are performing, right? So you're randomly picking up 85% of those observations, and you are getting 129 observations. And then you are also, yeah, samples may be replaced, but again, samples might be replaced, but again, you will have equally, I mean, the importance will be given to the one which are weak classifiers, the weak observations. See, see this trials equal to 15 is going to take care of that. It says that it is an adaptive algorithm, adaptive boosting algorithm. Fine. We also have got the reviews to be provided for the webinars in the session. So let me just show you all. Just a moment, please. So all you have to do is, I mean, this link is not opening. Let me just open in Google. So even if you just type XLR solutions, you will be getting the XLR. You'll be on the XLR solutions page over here. Towards the right hand side, you can see. Please click on that and provide your reviews and ratings about the session. Similarly, you'll have the Facebook page and the LinkedIn, wherein you can provide the reviews and ratings. So all you have to do is just log in over here and provide your reviews. Right. So that is it for today. We have a lot of parameters and arguments that we can fine tune. Yeah. You can just check with the concerned person, and he will be providing you the access to the recording session. All right then. Thank you all, friends. Thank you all for joining. Good night.